Hello. Now we're going to talk about research questions and hypotheses. These are, of course, the starting point of a research project, and therefore it's very important that they be thought out properly and carefully, and that the research be well-founded on a good hypothesis or a good set of research questions. As Virgil said, Felix cui potuit renum conoscere causas, happy is the person who's been able to learn the cause of things, and that is the motto of many different universities, including my alma mater, the London School of Economics. So, the research question. Well, we focus on founding a question, starting a question that can be answered in the appropriate time, and that will drive the research forward as we search for causal chains and links and an answer to that question. So really the research question is the epitome of what we want to know. It's the distillation of the things we need to know in order to drive the project ahead. So we need to learn the art of finding a question that hasn't been answered before, is tractable. In other words, it can be answered. It is possible in the available time and with the available resources to search for and find an answer, and that we have sufficient resources and sufficient organisation to be able to answer the question, or at least to provide a reasonable answer that will serve as the end product of the research project. So clearly we need a question that will lead to an answer that is useful, that drives forward the boundaries of science, however modestly it does so, and that generates insight into a problem, something that isn't trivial, but on the other hand, something that isn't so grandiose that it's impossible to answer in the available time. So we don't search for questions such as what is the meaning of life or does randomness exist, but on the other hand, we also don't search for questions to which the answer is obvious. Now, when you formulate research, one of the biggest hurdles to designing a program or a project is to find the right questions and assess whether they can be answered or not. Let's think of this as the funnel model. Now, if you take the upright funnel, you might think of a fairly general, a fairly large in scope question to be answered, and then try and whittle it down to something that can be done in the available time. Now, this is actually quite difficult, and it is easy to find yourself with something that is simply too difficult to do in the available time, biting off more than you can chew. So in fact, it's rather better to do a sort of inverse funnel approach, where you start off with a very modest question, and if it turns out to be too modest, then you upgrade it. For example, you study one village. If one village isn't enough, study two and make a comparison. If two villages still isn't enough, study three. But if you instead start by saying, well, I'll study the whole region full of villages, and then find you haven't got the time or the resources, then this is much more problematic. So very often we can see a world in a grain of sand. In other words, when we start studying that one village, we can see universal questions in it. And as we develop our research, we find that maybe we are looking at only a very small reality in physical, practical terms, but behind it there are some big questions to be answered. And we can make a modest contribution to understanding the answer to those questions. So, there are really two basic routes to research, although they are not mutually exclusive, and they can be used in conjunction with each other. Perhaps the more common route, or at least the more basic route, is induction. We proceed from specific instances to a more universal statement that unites them. So in induction, we gather together pieces of information, we find patterns in them. It's very much a look and see approach, and These days, it's very much favoured by information technology for the simple reason that we can do huge amounts of calculation very easily in very short spaces of time. Induction was less common when, in fact, we had to use manual calculation because computers didn't exist or they weren't powerful enough. And therefore, it was difficult to do things like data mining, which nowadays is very easy, where we can simply look through vast quantities of data, often called big data, and search for patterns and search for relationships and search for causal relationships. But the trouble with induction is that it is intellectually weak. It is by far the weaker way of doing things. It favours descriptive research, which is by definition low level. In other words, it takes longer, it is harder with induction to get to the causal relationships that really determine what is going on in the phenomena that we are studying. So, another factor, another weakness in induction is that it very often can only demonstrate correlation. In other words, that factors co-vary, but that doesn't necessarily mean that one causes another. So in a simple relationship, A might cause B, but in a more complex relationship, it might seem as if A causes B, but in fact A causes C, which causes B. Or in fact, of course, there are very much more complex versions of that with networks of causality. And induction might find the co-variation in them, but it is much less effective and efficient at finding the causal relationships. The alternative is to work deductively, and I would recommend to you that you move away from induction and towards deduction when you formulate your research, because deduction is very much more of a powerful methodology. So at this point, we start with an a priori universal premise. In other words, a hunch or a hypothesis about particular relationships. A causes B might be our hypothesis, or A causes C, which causes B, and things like that. And then we go out to test the hypothesis, the hunch, by looking at real situations, gathering data, and seeing whether the data, once analysed, conform to the hypothesis or not. So in fact, in many respects, this is much more efficient. If it isn't more efficient in computing terms, it is at least more efficient in intellectual terms, in terms of not having to think through things at a very low level, and in fact going right to the heart of a relationship right away, straight away. And generally, deduction is capable of arriving at a higher level of explanation. In other words, it is a sharper tool than induction. Now, when you do deductive work, you can do it either informally, in which you simply state a proposition, which is your hunch or hypothesis, and go out to find whether it's true or whether it needs to be rejected. Or you can use formal logic, in which we state a null hypothesis called HO, which says that regarding a causal relationship, there is no relationship between variable A and variable B. And then we go out to test that, and when we find that there is a relationship between A and B, then we reject the null hypothesis HO and we accept the alternative hypothesis H1, that there is a relationship between A and B. So, null hypothesis rejected, therefore the alternative hypothesis must be true and is accepted. Formal logic, by and large, is not particularly necessary when we're dealing with things that are not highly quantitative and that don't require a more general application of formal logic. So really, you can take the idea of the null hypothesis, or you can leave it in most social research. If you want to be more formal, then you can use this approach, but in many respects, it's not quite necessary. Now, Carl Hempel suggested that, in fact, there is a relationship between the deductive and the inductive approach, and he called this the deductive nomological route to explanation. We start with a set of initial conditions. Now, those might be obtained inductively. We look at them inductively perhaps, and we apply a set of appropriate laws that perhaps have been obtained deductively. And if we're lucky, if the laws fit, if there is pattern, if the pattern leads to causality, explanation is achieved, the event or the phenomenon or the relationship is explained. So we call that a Hempel loop, and it is a probabilistic inductive systematization, which is really rather a mouthful, isn't it? But it has deductive leanings to it. But then we need to verify or falsify relationships, and here comes in the work of Karl Popper. So really the work of these two philosophers of science, Popper and Hempel, show us that induction and deduction are separate routes to explanation, but they also can happen together. They can mix together because, in fact, it is very difficult to deduce anything without some level of induction. In other words, yes, you can have a hunch about a relationship, but not in a vacuum, not without knowing something about how things are disposed, as it were, on the ground. So, in fact, induction mixes with deduction. Deduction is the correct route to explanation, but it requires the induction of knowledge so that we know what we're talking about when we formulate a hypothesis. And we call that the hypothetical deductive system, and we might regard it nowadays as the normal model of science, and particularly natural science, and really, for that matter, social science too. So it tells us that you can't really do deduction without some level of induction, or you wouldn't have anything to deduce. So there are inductive steps within the inductive model, and these are the loops that take place when we formulate a hypothesis and go out and test it. However, if you swing too far towards induction and spend your time simply looking at data, wondering what they mean, then perhaps that is a sign of inefficiency that should better be replaced by a more deductive methodology. So one problem with all of that then is that inductively you might find correlation, but then the question arises, can you explain that correlation? Correlation simply means that as one variable changes, the other one varies, or the other variables, if it's multiple correlation, will vary in concert with the determining variable. However, as you can see from the lists on this slide here, A may influence B and C and C may influence each other, and all sorts of different loops in causality may occur. Nobody is suggesting that in the real world, so-called, causality is necessarily simple. And moreover, if you are dealing with a situation where there is a simple linear causality, A causes B, then it may not be very productive in research terms. It may be simply too basic and too elementary to be worth a research project. So we do spend quite a lot of our time looking at sophisticated forms of causality. For example, I am part of a research group called the Cascading Disasters Research Group, and we look at here at how cascades move through the system of interconnections between people and their assets and critical infrastructure and so on. And we often find that the greatest concentrations of causality are not with the triggering event, which might be an earthquake or a flood or a big storm or whatever it is, but often with the secondary consequences of that then go on to cause further disruption to the human system by means of escalation. So this brings us on to the question of feedback loops, and in both natural and social sciences, feedback is really very common and it deserves a great deal of study. Positive feedback is a form of self-reinforcing behavior, and as a result, it is transient. In other words, it doesn't last long. So what happens there, for example, in a hurricane is that evaporation causes air to rise where it condenses and then becomes heavier and falls and then evaporates and becomes higher and so on. So we get this convection system. And as it goes on and as it fuels itself from a warm ocean system, a warm ocean surface, then it can create the conditions for a hurricane. But a hurricane will not last forever because eventually the evaporation condensation system will break itself and the hurricane will disperse its energy and it will die out. So positive feedback in general is not something that lasts more than a determined period of time. Negative feedback instead is a self-correcting mechanism in a system. Again, it could be a human or a physical system. And what it tends to do is create homeostasis, the tendency for a system to react to shocks by returning to an average value. So this is the self-correction in the system. We have to be careful when we apply this to social sciences because the assumption in negative feedback and homeostasis is that the system has a constant mean. What we find in society is that instead it is constantly changing. So in fact, rather than a steady mean, we tend to have a trended mean, or at least we have changes that reflect a trend. Population, for example, in most places is growing. And therefore, it's difficult to make generalizations based on a steady, stable population, even when there are shocks from it, because they instead refer to a trending or a growing population situation. So negative feedback is useful and it helps keep systems on track through homeostasis, and it is a very natural tendency in many different kinds of system, but we have to treat it with some caution because of the possibility that there isn't a stable mean. Now, you've formulated a hypothesis and you do your research on that basis. You go out to find, by collecting and analysing data, whether the hypothesis is true or false. Now, you don't need to have necessarily only one hypothesis. Supposing, in explanation, there are several possible alternatives. So we therefore can use the process of multiple working hypotheses, where we search for alternative explanations, and when we've done the analysis of the data, we accept whichever hypothesis is the most likely one. For example, in a piece of research I did, I was confronted by the fact that I needed to explain the deaths of people in an earthquake in relation to the demographic pyramid, which is stratified by age and by sex. So what I found there was that there was a disproportionate number of elderly women over the age of 70 who had died in the earthquake. And I needed to find out why this was. And I was lucky enough to have behavioral data and information on how people had died in the earthquake. So I set out with a series of propositions, which we might call the multiple working hypotheses. For example, that men were in one part of the house and women were in the other. Men were watching television, women were washing the dishes, or something like that. Not very plausible. And in fact, it turned out to be quite rejected. In the end, out of all the possible explanations, of which there were about 5, of why there were more women than men, we managed to light upon one, which was that women treated the house more as a refuge. Men were more sceptical about that. And after some foreshocks before the earthquake main shock, when everyone went outside, more women went back inside and more men stayed outside. And this was our explanation. Other explanations based upon other forms of perception or behaviour were therefore rejected. Now, that's very much a statistical relationship. Would we call it a scientific law? I think not. In physical sciences, it is easier to determine laws because they are verifiable regularities. And when you see something like Boltzmann's law or Avogadro's principle or something in physics or in chemistry or whatever, then it generally is true under all circumstances, at least on the surface of the Earth. So scientific laws are easier to derive and verify in harder sciences, and if we rely on laws at all, on simple statistical regularities in social behaviour, because society, by and large, doesn't generate laws in the same way. So in many respects, if you ever see a reference to a law in the social science research, it's more of a pseudo-law, at least judged in hard science terms. Instead, we're much more attuned to working with theories. And in a theory, we have derived a regularity and we believe that it is true. But on the other hand, we have no means of verifying every instance. Now, for example, people in the Northern Hemisphere before travel became easy were convinced that it was effectively a scientific law that all swans are white. And the first travellers to arrive in Australia were immediately confronted by black swans, and that more or less destroyed the theory, which appeared to have been a law but wasn't, that all swans are white. So when we make a hypothesis, we're effectively trialling a theory. In other words, let us see whether there is a regularity. We state the regularity as a proposition, and perhaps it is a causal regularity, and we go out and we test it. We might do so in terms of formal logic as a syllogism. So here is a simple syllogism. The weather's warmer in summer, more ice creams are sold in summer, therefore there is a causal relationship. People buy ice creams because the weather is warmer, and it seems a perfectly reasonable assumption. So in a case like that, the causal relationship is fairly simple, it's fairly easily tested, and it's fairly easily verified by both logic, and you could go out and you could ask people why they bought an ice cream. And you could also count the number of ice creams sold in winter and in summer, and therefore verify your hypothesis. What about a fallacious syllogism, however? The weather is warmer in summer. People buy winter clothes in summer, therefore people buy winter clothes because the weather is warmer. Well, it isn't true, but on the other hand, winter clothes are sold more cheaply in summer, and that's why people will go out and buy them in preparation for the coming winter when the weather is still warm. So we need to look quite deeply at certain hypotheses, because there is a risk that the superficial approach will give us the wrong answer. So let's do some frequently asked and frequently answered questions. Firstly, can one have hypotheses in non-quantitative research? Research doesn't have to be quantitative, it can be semi-quantitative, qualitative, or a mixture of these. And yes, most certainly we can have hypotheses in non-quantitative research. We have to think carefully, though, if we do, about exactly how we verify the hypotheses, which may be a little bit harder because we need to use non-quantitative means. We don't end up with a number that tells us the hypothesis is acceptable or not. Not that numbers necessarily are the be-all and end-all of hypothesis verification. In fact, many of the rules of using statistics to verify hypotheses are actually entirely arbitrary. A good many of them, in fact, were derived whilst observing the growth of turnips in a field at Rothamsted, Hertfordshire, about 100 years ago at the Rothamsted Experimental Research Establishment, where in fact many of the early statistical methods were developed, and they were transferred to other forms of science with little debate about whether 99% sure or 95% sure actually has any innate meaning when we're dealing with other forms of hypothesis. So another question is, do I have to have a hypothesis in my dissertation or in my research project? And the answer is, well, it's often a good idea, and it certainly helps to focus the research, although a less focused, more general research question may be sufficient And in deciding that, one needs to look at exactly what is being studied and what the potential for having a good hypothesis is. So you have to use research judgment to decide whether you want a hypothesis or whether you will go with a research question alone. Of course, you can have both. You can state your research question and then turn it into a hypothesis so it is more easily accepted or rejected on the basis of the analysis. In other words, you pose a question and you turn it into a proposition to be tested. So in either case, you do need one or the other or both. You do need a research question, you do need a hypothesis or some combination. Is it wrong to do inductive research? No, a great deal of inductive research is done these days thanks to use, one might say overuse of computers. And in many respects, inductive research is very often low-level and therefore uninspired. Does it push back the frontiers of science? Well, if it does so less and slower than deductive work does. Deductive work is very much more the cutting edge, and please remember that when you formulate your research. Can I be sure that my hypothesis is both non-trivial and solvable? The answer to that is you can't, but any research that is worth doing involves some risk. Now, we try to constrain the risk to be sure that we get results and we end the project happily rather than with some non-committal, incomplete, unsure half answer to our research problem. So you have to use judgment in this and your feel for what can be done and what is a good question to answer. And of course, a good proposition to state if you are using a hypothesis. And one fortunate let out for this is that at the end of it, if your hypothesis isn't working, you can often go back and rejig it and restate a slightly different hypothesis on the basis of your analysis. So although in formal terms and definitely in the write-up, we work forwards. We have a hunch, we state a hypothesis, we collect data, we analyze the data, and we conclude in order to reject or accept the hypothesis. In reality, when you go out and do research, you can work backwards as well as forwards in the way that as you write a dissertation or a paper, you probably write the abstract, if not also the introduction, last of all, because at that point you've got something to write a summary of or to introduce. Whereas, of course, the reader of the paper will see these things first. So another question is, what should I do if my results don't turn out to provide a positive correlation? Supposing I've made a hypothesis to say that A is the cause of B and the analysis shows that it simply isn't. Well, at least in theory, negative results are perfectly acceptable. They are a contribution to science because they tell us, well, don't go down this route again. I've been down this route and I found that A does not cause B, therefore there is no need for you to repeat that research and come to the same negative conclusions. And that is a gift to other scientists in many respects. On the other hand, a piece of research that comes to negative conclusions is really not as attractive as one that says, yes, there is a relationship between A and B, and I have discovered it. So usually, however, when you find that there is a negative relationship, when A and B are not related, then there is an alternative relationship that you can state and recover your position as the purveyor of positive knowledge. Let's remember here, I'm not talking about inverse relationships where an increase in A causes a decrease in B. That is still a relationship. What I'm talking about is a situation where there simply isn't a causal effect from A to B. So what do you do when you're doing your research under the expectation that there be a relationship, and you find that, well, there might be or there might not, but the way that the data have been collected and analysed, the way the hypothesis or the research question formulated, simply doesn't arrive at an adequate answer. So this, of course, is rather difficult, especially in the write-up, and the best thing you could do is keep your eyes open for signs of this when it begins to happen and change direction towards something that is more promising. So there are many instances when research is a blind alley, and that is unfortunate, but it is also a fact of life that we may apparently see a very promising relationship to investigate, but when we start to do so, we find that we simply cannot get the proof that the relationship exists for one reason or another. It may be impossible to get the right data, or the data that we get may simply not lead to the establishment of a definite causal relationship. So when that begins to happen, the best thing to do really is to try to change direction towards something that looks more fruitful. Why can't research be purely descriptive? Well, we do have descriptive research, but really when we do scientific work, we want to arrive at a higher level of explanation. Description involves simply putting facts together, putting data together, and it is the lowest level of explanation. It doesn't really find the more sophisticated and the hidden causes in things, and it may push the frontiers of science forward, but in such a minuscule way that we don't get very far with it. Now, description is often a very essential early part of the research process in order to understand what we're dealing with. But then we need to go beyond mere description and look for the mechanisms, build the models, and look for the causal relationships that give us a handle on what is really going on out there in the world. Now, when you do so, there is one thing to bear in mind, and that is sometimes known as Occam's razor. William of Ockham was a monk who lived in Ockham, not far from Esher in Surrey, in the 12 and 1300s, and he said, "Entia non sunt multiplicanda preta necessitatum," which means use the simplest model you can get away with, because the simplest model you can get away with will not be disproved by the data. It's a way of saying don't overcomplicate. Now, you have to use your judgment as to what is overcomplication. However, everyone will thank you for using the simplest model. Simplicity is elegance. A good model will take out the noise and leave the signal, if I may use a metaphor derived from electrical engineering. In other words, it will go down to the essentials of the relationship and remove the obscuring factors that aren't necessary to know. But the very best models, the most elegant ones, are as simple as they can be without betraying the relationship. And that is something that will always be useful to keep in mind as you do your research.